Well, hello there, folks. Hope you like that cool introduction. My name is Ron Pratt. I'm an associate professor here at Fresno Pacific University, and I mostly teach mathematics classes, but I've gotten quite interested here in the last few months in computational quantum mechanics. It's full of lots of interesting math and interesting applications as well. What I've done here is I've taken the classic helium hydride example and done it on Mathematica, using Mathematica software. Now this is the example you find in the classic text. Szabo and Ostlund, hold it up here where you can see it. I was lucky enough to get this textbook used off of eBay, the old hardbound edition. It's also available now in a Dover edition, softbound, so it's very inexpensive. And I've gone through a lot of material on HartreeFock, and in my opinion, Szabo Ostlund is the best textbook by far. The equations are derived for you in a very clear and complete method, and everything is done so you can actually use it. Going through textbooks and YouTube videos, almost felt like there's kind of a conspiracy out there to give me some kind of glittering generalities on the HartreeFock method, but then I want to actually do it myself. There's just not enough material there. But Szabo and Ostlund certainly gives you what you need to do your own HartreeFock calculations and get started in it. So it's my favorite reference for sure. Also a good reference here is a book by Charles Quinn. He does a lot of computational quantum mechanics using basis sets, and does it using Microsoft Excel, which is quite an amazing thing. The narration, the text in the Quinn textbook's a little terse, a little hard to get through unless you have a background from Szabo and Ostlund, but the examples are excellent. And I may try and set up a few YouTube videos in the future doing some of his Microsoft Excel examples and doing them also on Mathematica. So those two textbooks, Szabo and Ostlund and Charles Quinn, those are the two textbooks that I found really helped me in learning something about computational quantum mechanics. We're going to set up here this classical example for the helium hydride ion. We're going to do it using Mathematica software. The reason I like to use the software is that I can kind of just use it like a big calculator. I don't have to do a lot of fancy programming. You don't have to master a lot of syntax. You can pretty much just type the equations in directly like you see them in the textbook and in the references. So it just makes it really clear and easy to do the calculations. In Szabo and Ostlund, page 146, he gives a 12-step algorithm that takes us through the setup and through the calculations of the self-consistent field method. So I've numbered these steps also 1 through 12. You can see the number 1 comment step up here. So we're going to do number 1 in this video, and then 5 subsequent videos we'll go through the remaining steps for a total of 12 steps. So hopefully it'll make it really clear and complete so you can actually do some of these calculations yourself. If you want to, of course, you can take screenshots of the page as we go along. You can stop the video and type in the text if you want to type this into Mathematica yourself. So I hope that'll be useful for you. Let's go ahead and get started here. I'm going to kind of awaken these lines as we get through it here. I've put them in a black background, and then I'll wake them up as we get to them. So let's start here. Here's the first part. Step 1 in the page 146 Szabo procedure is really just reading in the data and problem setup. So that's what we'll do in this video. So first thing is just information for the helium hydride ion system here. We have 2 electrons, so we'll call that n equals 2. We're doing a minimal basis set, so we're going to have a Slater type orbital approximated by Gaussians on each atomic site. So we're going to have 2 members of our basis set, 1 for each nuclear location. So in Szabo he calls that variable k, so we'll call that k equals 2. And then we're going to approximate our Slater type orbitals using a contraction or a linear combination of 3 Gaussian type function. So it's an STO3G, so that 3 here is represented by L equals 3. His example is set up for what's more or less the bond length of the helium hydride ion, 1.4632. I just use that example because that's what he does in his example, and this way we can compare the numbers we get as we go along. Normally you wouldn't know what the bond length is until you have already set up this program, and then you would run a HartreeFock self-consistent field program for different nuclear separations, and then the value for which you get a total energy at a minimum, you take that to be your bond length. So we'll just borrow this number 1.4632 that Szabo uses in his example, and we'll use it too. The charges of the nuclear sites for the helium will be a Z value of 2, for the hydrogen a Z value of 1. So that starts our setup procedure here. Let's move on to the next cluster. Let's go and make this visible so we can see it. So we're using the Slater type orbital 3G representation for the Slater orbitals, and these are the values. I think a guy named Popple came up with these numbers, did a least squares fitting linear combinations of Gaussians to emulate exponentials, emulate Slater type orbitals, and these are the numbers that you get out of tables. These came from equations 3,219 through equations 3,221 in Szabo and Ostlund. These numbers are fixed. You type them in, you get them off a table, or you get them out of a database. They do not change. They're just data that you read in, and we'll just carefully type the numbers in here. Alphas are the exponent constant values, and the deltas are the coefficients in front of the exponentials. We have them for site 1, for site 2. They're both hydrogen 1s type orbitals, so in this case it's the same numbers for 1 and for 2. So there we are. Just type them in. They're fixed. They won't change for the duration of the program. Next we'll take the Slater orbital exponent values here, the zeta values. Got these from the Fortran code in Szabo and Ostlund. These again are fixed. You can get them from various references. I just took them out of his example Fortran code in the text. So zeta 1, zeta 2, there they are. If you're doing this on Mathematica, each one of these cells, when you want to actually execute it, you want to do the computations, you do a shift enter. So I'll do that here, get us caught up. All right, let's move down, take a look at the next cluster here. Let's remove the coloring. And here we need to normalize and scale to the zeta values that we're using. These are using equations 3,224, 3,203 in Szabo Ostlund text. It's just getting the these values you've looked up out of a table somewhere and getting them scaled for your problem, so things are orthonormal with respect to each atomic site. So there they are. We'll do that and do the calculations and scales them here appropriately, and these numbers should compare with numbers that are given in Szabo and Ostlund. So yeah, we're on step 1 here of this 12-step procedure. We're just getting things set up, ready for us to go here. Let's move on. This I put in just to kind of do a little check here so I can compare my Slater orbital with my Gaussian approximation to it. So for one thing, this will help weed out any typing errors. If you mistype some of the numbers, you'd hopefully be able to discover at this point. So Slater 1, that's the Slater hydrogen type 1s orbital that I'm actually wanting to use for this basis set, but I'm approximating it for ease of calculation, so I'm approximating it by a linear combination of 3 in this case, Gaussian types, e to the minus r squared. So just want to compare the two here, see how good our Gaussian approximation is, and you can see it's it's pretty good. There's two big problems here. You're trying to use Gaussian type functions to emulate exponentials, and that's that they die off too quickly. You can see that's not a problem here, taking suitable linear combinations that Popple worked out, where the two functions agree very nicely here. We do have a bit of a problem here for excuse me, for small values of r. Our Gaussian functions are always going to have a 0 first derivative, whereas we really want a cusp for our Slater type orbital. So there's a little bit of a gap here. It's not a big problem, and presumably if we used maybe a Gaussian contraction of 6 rather than 3 or 10 even, we'd reduce this error a lot. But for an STO3G, that's as good as we're going to do. But it's okay. It's in the ballpark. It's going to certainly be good enough for this illustrative calculation. And then I did the same thing for the other orbital site as well. And nothing's really changed here. It's just scaled differently for the different atomic orbital, but you can see the same issues here. Everything's really good. Our decay rate is emulated really nicely by our Gaussians, but our low value of R, we do have a little bit of a discrepancy here between our approximation and the real deal Slater. But again, that's what you expect with a STO3G, so we'll go ahead and do that. So there we are. There's step 1 of 12 done. We're ready to move on to step 2, which I think is the longest of the 12 steps, calculating the 1 electron, 2 electron integrals. We'll do that in the next video. But there we are. We finished step 1. Thank you for watching. I hope you find this useful, and I hope to see you in the next video where we will now do step 2. Thank you. Bye-bye.